welcome everybody to this other installment of Ithaca seminar series, and I'm very happy to have Filippo Bonchi today here from University of Pisa, and so I'm very curious to see what happened in Hawaii 5 years ago. And and so what's up with the deconstructing Tarski calculus of relation with tape diagrams? So Filippo, it's yours.
Thanks a lot, Giuseppe. So indeed, this work. I started to think about this a long time ago. I was visiting Dusko Pavlovich in Hawaii, and there was also Pavel. And yes, basically, I was studying a bit some structure in REL, and yeah, we thought there was nice intuition and some cool way of drawing things around, but yeah, nothing formal. And somehow I put these notes in a folder and didn't look at them until December. And since December, I'm working actively only on this thing. So it's I'm quite excited by this work nowadays. So let's say that the calculus of relation works as a main motivation, let's say a leading example, but tape diagram in my own view go much farther, and I will show you, if I have time, like some way to use them to make quantum control. So, but let me start with the calculus of relation by Tarski. So Tarski introduced this in 41. It was somehow an alternative to first order logic, which is based on relation. So he fixed a signature sigma with which are basically relational symbol with arity 1 and coarity 1. So these and we denote them by R, S, and T, and these are basically interpreted as a binary relation. And then define a set of expression in usual this kind of context free grammar. So it's say either is one of these relation belonging to the signature, or you have the composition of two relation, or the identity relation, or the bottom, the union, and this is the clean star, so the reflexive and transitive closure. This was not in the original work by Tarski in 41, but has been added later on, I guess, by cleaning, and this make the calculus of relation even more expressive than first order logic. You can express things like reachability in a graph. Okay, then you have the top relation, intersection, and then you define the opposite of a relation, and then the negation. Okay, you can express really lots of cool things with this language. For instance, you can express when R is a function. So basically, do you have any guess? I want to say that 1 is included in R compose R op, and this should mean that R is total, and then R op compose R. So basically, this is like to say that R is a left adjoint. I guess you have seen these things many times. So that R is a left adjoint and R op is its right adjoint. Okay, the main question here is the semantic equivalence. So to define the semantics, first define a model, which is just some set X with a relation rho of R for every relational symbol R in the signature. and the semantics is defined, I mean, how the more in the expected way. And then the problem is the one of semantic equivalence. So I want to check when two equivalents are equal with respect to all possible model. And this problem has been studied for many years, and is actually studied a lot by I mean, in computer science conference, there is always some paper about defining algorithm to check this equivalence or axiomatization for fragment of this, because it's known that you cannot. Okay, even if you drop the negation and the star, so actually, if you drop the negation, then this equivalence is decidable, but there is no finite axiomatization. This has been proved. So let's see some axioms, for instance, but these are not complete, as you can expect. So for sure you have that those of Boolean algebra. Then, for instance, we know that this fragment here is what is called a Kleene algebra, while this fragment here is what we are called allegories. And for instance, other axioms are those who tell us that the composition distribute over the union, while the composition only distribute laxly over the intersection. Okay, so for the rest of the talk, I will drop the negation and the negation and the reflexive and transitive closure. And I will mostly focus on these two fragments. So the Kleene algebras, which can be thought as categories with finite by product and trace, and allegories, which I will use. I'd rather use Cartesian by category to talk about them. And let's say that the nice things about these two fragments is that these two fragments characterize exactly the two different monoidal structure of REL. So we have, REL carries two monoidal structure. So REL with disjoint union and the empty set. And in this case, the disjoint union is a byproduct in REL, in the sense that it is both a product and a coproduct. And when one observes this, one can easily give a language of string diagram, which basically consists of bang, diagonal, co-diagonal, go-bang, co-bang, and then you have the usual structure of a symmetric monoidal category. And then you require that some axiom hold for this. So you know that this form a commutative comonoid, this is a commutative monoid, and you know, for instance, that the monoid and the comonoid interact as a bialgebra. And this is because in general, in category with the product, both the monoid and the comonoid have to be natural with respect to any arrow of the category. So we say that any arrow is a monoid and a comonoid homomorphism in this sense here. So for instance, I can express the previous law, so the distributivity of composition of a union as this diagram here. So this gives me the union now, and so this is R composed with S union T, and this is just, I can just use naturality to pull R inside, to copy it twice, and this is just R composed with S union R composed with T. So I told you there was two, so these are finite product category. And then I have now here allegory, so Cartesian by category, and these are exactly rel with times and 1, where times here is not the categorical product, because in rel, you know, it's disjoint union. Here I mean really the Cartesian product. So you have exactly the same structure, but the structure obey to different laws. And these are the laws of Cartesian by category. So again, you have a comonoid and a monoid, but they don't form a bialgebra anymore. They form a special Frobenius bimonoid. And then naturality doesn't hold anymore, but only hold lax. So you have lax naturality. And then you have this nice adjoint axiom, which tell you that the comonoid is the left adjoint to the monoid. And for instance, if I want to prove now that if I go and interpret this diagram in rel times, then this becomes, this becomes the intersection. And yes, this, so this as well. And but now I don't have naturality anymore. I have only lax naturality. So this is just an inclusion. Is this okay? Is everyone has some question? Anyone, or is all clear?
I have a question.
Yes.
So I think you and Pavel have a paper about relational syntaxes.
Yes.
Is this the same thing that you are presenting here, or it's different? And another question, is this also connected to the paper of Chad Nestor, which recently popped up about semantics for relational structures?
No, I mean, let's say this is a continuation of both, in the sense that what we have done with Pavel so far was always to consider just this, and not the structure. And so what we could express in terms of relation was just this, and in terms of logic, this would be regular logic, while what I'm going to do now is going to be coherent logic. So before we only had existential quantifier and top, and now I'm going to add or a bot.
Thank you.
This I haven't understood yet the relationship with the regular categories as they are in the book, but I guess there is a close connection.
I have a question as well.
Yes.
I don't see in those diagrams the modular inclusion law. Is there any diagram for that as well?
So the nice thing is that the modular law can be derived by these axioms.
Okay.
So, and Bob Walters, who introduced Cartesian by category with Aurelio Carboni, was really pleased by this modular law, and he was saying that it was kind of you really used the Italian word formiche mentali to mean that it's like some kind of wrong axiom, that the right axiom are this one, and you can easily derive the modular law. If you want, at the end, I can also send you a reference to his blog where he talk about the modular law and how you can derive it through these axioms.
That would be great. Thanks.
Yes. So okay, we have these two structure. So you have rel plus and rel times, and we would like to put them together. Actually, they have much more in common than just being two symmetric monoidal structures. They also have two monoid and comonoid, which kind of interact in an interesting way. So I want to put these two symmetric monoidal structures together. So the formal tool is to use rig categories, but also I would be interested to depict the expressions of these rig categories. And there has been quite some work on this problem. In particular, there is this paper called the sheet diagram. But I kind of don't like this so much, and I strongly prefer this tape diagram. More generally, since lots of people started to use the string diagram, you see more and more paper who use like a mixture of algebraic notation and diagrammatic notation, because somehow the diagrammatic notation seems not to be enough. Like there is this paper by Robin Piedelou and Guillaume Boisseau, where they introduce mu sup prop, where basically they do with they need circuits, but then they also need this some algebraic syntax to make things work. But also, if you look at the book of the ZS calculus, but many other papers, they often use notation like this with some diagram here to mean like a linear combination of diagrams, of string diagrams. So tape diagram allow to avoid this and to draw basically everything and make all how to say all proof in a graphical way, so that many of the axioms are somehow embodied into the graphical notation. So on the other hand, we need kind of a restriction. So we require that the plus, so in a ring category we have plus and times, and here we require that plus is a byproduct. So plus would always be a byproduct in tape diagram. So one could also require plus to be a coproduct, or even a product, and this would also be okay, but the language would not be any more universal. Maybe I will come back into this later on. But I mean, okay, these rig categories where plus is the coproduct are called distributive monoidal categories. So there are lots of examples, but also when with the rig category where plus is finite product, you have rel, you have matrices over whatever, finite Hilbert space, and so on. So it's quite convenient as a language. So the main idea can be expressed by looking at these two adjunction. So if you have so these are all strict. These are all so here the monoidal structure is strict. I'm strictifying everything. So in particular, let's look at the forgetful functor, which go from a finite byproduct category to a category. This is a left adjoint, which basically map any category C into a finite byproduct category, where objects are basically strings of objects of the original category, and arrows are the diagram generated in this way, where here I have this F is somehow an arrow of the original category. So I put this F around a tape, and I look at this as a basic string diagram, as if it was somehow a symbol of my starting signature. And this gadget here gives me the structure modulo the axioms, for sure, modulo the axiom of a finite product category. This give me the structure of a finite product category. And I have also to require two more axioms. So basically, I have to require that this taping is a functor, so that the tape of the identity is the identity, and that the tape of a composition is the composition of two tapes. The unit of this adjunction, so is what we call the taping functor. So it basically maps an arrow f into the tape of f. So, but what happens if now I start from asymmetric monoidal category M? I forget about its monoidal structure, and then I apply F2. So we have that this category is a finite biproduct rig category. So the plus is a finite biproduct. And I also have a times. And in particular, if I start with a monoidal signature sigma, and I take C of sigma to be the symmetric monoidal category freely generated by sigma, if I do the same trick, so if I forget about its monoidal structure, and then I add freely by product, this is the finite biproduct rig category freely generated by sigma. Here I should mention what I meant by universal. By universal is, I mean, somehow here we are using a trick, and the trick is that I start with a monoidal signature, while in general, when I'm interested in rig category, I would like to have a rig signature. So a rig signature as can let's say have as arity and coarity expression which involve both plus and pair and times. This is what is called a rig signature. But the point is that once you have the finite biproduct in your category, you can always reduce a polynomial, a rig signature to a monoidal signature. Pretty much like in Cartesian category, you can always reduce a monoidal signature to a Cartesian signature. It's exactly the same idea. So basically, this gadget here allow you to always reduce to the case where you have where your symbol have you only one input and one output. Not sure if this is clear, but if not, I can go back on this later on. What else should I say? Yes, that these axioms, this theorem trivially also if one consider finite product or finite coproduct categories, and also that to make this nicely, we had to fix some issue on strictness, and we think we did in a rather cool way, but I don't really have time to enter in details now. So let's see how we draw them. So the idea is that so we start with a set of basic sorts which call A, B, C, and so on, and we have some symbol from the monoidal signature, and we first build the circuits. And so circuits are built in this way. And you see here the parallel composition of two circuits is just the times. And this gives me the category C sigma, so the category of string diagram. Whereas you know the objects are string over the set of basic sorts. And now I can do tape out of it. And basically, what are tape? You can think to them as string diagram of string diagram. So within you have a string diagram, and within a string diagram you have possibly another string diagram. So a a circuit. So it's like a two-layered syntax. So now here objects are string of string, and this is indeed F2 of U1 of C sigma. So I forgot about the monoidal structure of C sigma, and then I build this again. The point is that now when I compose in parallel two tape, these tape are in plus and not in times. And this way I can represent in 2 dimensions both plus and times, which we find quite nice and intuitive, rather than having 3-dimensional representation, which are quite heavy to draw and parse. Let's see some example. So these are like 3 tapes in parallel, and these tapes contain the identity of A times the identity of B. This contain the identity, so it contains nothing, so it's the identity of 1, and this contains the identity of C. So this is the identity of A times B plus 1 plus C. This is a symmetry of plus. So this is a symmetry of plus, which is swapping A, B1, and C. So A times B plus 1 and C. While this is an identity of times within a tape, as you expect. So this just swap me A times B times C into C times A times B. So this is A, B, C. This is another natural ISO, which in the category, because of the strictness issue I was telling you, you cannot throw away, but it's an interesting one. It's called the left distributor. So the right we can strictify and becomes an identity. The left you cannot strictify in general. And this basically go from A times C plus A times D plus B times C plus A times D into, I mean, you're swapping into A times C. I mean, you know, and this, I guess, it's A plus B times C plus D. I guess. And okay, and then general, I mean, more complicated symmetry of times. You obtain them by composing this left distributor with the symmetry inside tapes. Okay, so I mean, the main, I mean, one of the main results is to show that this category is a Rig category, because the way we define is only a finite by product category. So we basically have to define on top of the structure a times, because here we have only plus. And the way we define times is exactly like Kronecker product of matrices. So this, I don't want to explain you how we do it, but the proof, I would say, is really elegant. It may look a bit complicated, the product, but the nice thing is that we can always forget about the product, because when we do graphical reasoning, axiomatic reasoning, we prove at Iono that we never need to decompose with respect to the product. So we can make all our manipulation without knowing what is a product. And okay, these are substantially the axioms. So these are the usual axioms for symmetries in a monoidal category. These are the axioms which tell us that this is a monoid, so this is a monoid, the axiom of bialgebra, and these are the axiom of naturality. And so the axiom of monoidal category for both C sigma and F2U1 of C sigma are implicit in the diagrammatic representation, and also these two axioms that I showed you before. You really draw these things in the same way. In the same these and these and these and these have the same diagrammatic representation. These are those axioms which we need to use from time to time. Okay, our interest in tape diagram go far beyond REL. They're like Petri nets, linear logic, non-convex algebra, imperative program, quantum programming, and so on. But the nice thing is that we have lots of languages based on string diagram. So their syntax is usually given as a symmetric monoidal category freely generated by some signature sigma. And then there is a semantic domain, which can be finite Hilbert space, matrices, or whatever. And then you have a functor from the syntax to the semantic domain, which is the semantic map. Okay, now if the semantic domain carry the structure of a finite biproduct ring category, the semantic map extends uniquely to another semantic map, which now assigns semantic to tape diagram. So for instance, what I can do, I can take this to be the syntax of the ZX calculus, this to be the category of finite Hilbert space, and then I can build tape for ZX calculus and get semantics out of it. And for instance, in this way, I can express control in quantum programming language, which is not easy with the ZX calculus. And you can see this is, so basically we are using a dialect of ZX calculus introduced by Miriam Bakans, where you can express scalars. So you can express 0 and 1, and this tape diagram is what is called the controlled U. So imagine U is some ZX circuits, unitary, and here you have a qubit of control. If the qubit of control is 0, you should do nothing, so you have the identity. If the qubit of control is 1, you should do U. And if you basically compute the semantics, as I told you, with just taking the semantic of Miriam and applying the taping like this, you get really the semantics of the controlled U, which I write here in the bracket notation. I can also express some sort of axioms. These two are axioms for expressing that 0 and 1 form an orthonormal base. This is saying that basically 0 plus 1 is equal to the identity, and this is saying that basically 0, 0. So this is the this is this. Wait, I'm a bit. I always do. Yes. So this is the state 0, and this is the effect 0. So this is equal to the identity, or also 1, 1. while this is saying me that 0, 1 is 0 and 1, 0 as well. 0 here, I mean the 0 scalar, which is this one here. I mean, since you have finite byproduct, this category is enriched over commutative monoid, and for sure, you know, this tape is, I mean, let's say you have C and D here. This is C plus D, and this is the 0. Okay, and then I can, for instance, I can show you a graphical derivation that if I have my qubit of control is in the state 0, and I apply this to the controlled U that I was showing you before, then here I can use naturality, and I can push this 0 here and here. At this point, I have 0, 0, which thanks to these actions basically disappear. While here I have 0, 1, which is equal to 0, so it cut the tape here. And now that I've cut the tape here, I know that by naturality of the bang, I can erase U and E, and then by the fact that bang and cobang are the unit and co-unit, I can just get this one. Okay, let's come back to REL now. So for REL, it's enough to take as a starting category the Cartesian bicategory freely generated by sigma. So this is basically this one, and the axioms are those that that I show you at the beginning of the talk. But I have to put them into type diagram, so they are basically these axioms here. So, and these actions are, okay, those for symmetric monadal category, comonoid, monoid, special Frobenius monoid, lax naturality, and then adjointness. And the nice thing is that I need to add some other axioms, but which now say that this, that the monoid of plus is left adjoint to the comonoid of plus. While here, for the monoid of times and the comonoid of times, we have exactly the opposite adjunction. So the comonoid in times is left adjoint to the monoid, while in plus the monoid is left adjoint to the comonoid. So you can see that this is this. So basically the things is reversed. This is this, again with reversed. This. So now it's kind of so maybe I've been even too fast, I'm sorry. So let's go back to the calculus of relation by Tarski. So what I'm going to do, I translate R as a tape with a single box inside R. If I have the composition of two expressions, I just make the composition of the two translation. One is the identity tape. Bottom is just the 0. The union, I need the diagonal and codiagonal. Top is this one, and intersection is just I now use diagonal to codiagonal of times, and then for the opposite, it's the usual things you do with Cartesian bicategory. So, for instance, okay, if I encode into the, so if I use this encoding, this tape diagram is just the representation for the expression R composed with S union T, and this for the expression R composed with S union R composed with T. While this tape diagram is R composed with the intersection of S and T, and this is the tape diagram for the intersection of R composed with S and R composed with T. And okay, this is a very simple derivation to show this this law of I don't remember how is this called, absorption. Yes, I think so. So we first proved that R is included into the R union R intersected with S, and this is trivial. So you have your tape with the R. You can add this unit. Then you know that by naturality of this, you can add whatever here. And then by the fact that these are adjoint, we can just glue this together. So here we are using these axioms here. The other direction, let's say I want to prove that, so I have now R union R intersected with S. I want to prove that it is included into R. So this is my starting tape diagram. I can just add to R. I can do this because these are the units, and then I can now, by naturality, I can push this stuff out here, and this one as well. So I end up in this situation, and now this is stop. Oh no, wait. First, I can push again by naturality R here and here, because I have R here and here, so I can push it here, and then yes, S is smaller than this. This is an axiom. I mean, I don't know if it's an axiom. It can be derived easily. See, yes, it can easily be derived by this. And now, okay, I can push this and this, and end up with this, and then this is equal to this. Okay, and yes, that's basically all. I think I've been too fast, maybe, but my talk finish here.
Okay, thank you, Filippo, for your presentation, which was very clear and well. So we have time for some questions or comments by the audience, if anyone would like to.
Can I ask a question?
Yes, sure.
So thank you very much for the presentation. So in our paper, Fosco and I and Pavel, we have something that we call Fox theorem for restriction categories, and so this is like this is similar to what you do, but we mostly work with partial theories, so it's much less expressive than your framework. I was wondering, do you think you could have some form of Fox theorem? For, of course, you need a different notion of restriction categories, but do you think there is chance to have it?
Not sure I understand your question, in the sense that when I start to say that since the very beginning that finite product category as this structure, I'm using Fox theorem. This is right. Here I'm using Fox theorem. So basically, you know, by Fox theorem, you know that if you have a natural comonoid, you have product. If you have a natural monoid, you have a coproduct.
So you're saying
they are
that
for the same structure, then they are really a byproduct. It's really little check. That's what I'm using here since the beginning. Then I don't know what are you referring to, if there is something more. But,
yeah, there is actually a bit. So in our paper we call it Fox theorem, but we actually are showing something a little bit sharper. But here it would be too long to enter in this debate. But I mean, this is a partial answer to my question. So thank you.
Okay, let's say that maybe I mean, for one monoidal structure is trivial. If you want to say I have both, one need a few. I mean, if one really want to consider the category, all the category, let's say where you have plus and times which behave as in rel, you need a few more coherence action which explain you how to build, for instance, the.
Yeah, that's exactly what I mean. In a sense, you can let's call them for a second Cartesian rigs, even though this is not a good name, but let's give this name. Yes, the question is whether there is a left adjoint from Cartesian rigs, sorry, from rigs to Cartesian rigs, so that you can force both the monoidal structures to interact. And there should be, by the adjoint functor theorem, essentially. And the way you should construct it, I guess, you take something like Frobenius objects in your rig, and this should be the Cartesian rig that you are looking for, because this is how Fox theorem works. But I mean, this is, I'm just saying random stuff here. Maybe it doesn't work.
Yeah, I guess it's something like this, yeah.
Thank you, Ivan. Are there any other questions or comments?
Yes, I do have another question. When you were talking about RAL, if I understood this correctly, you're basically talking about the theory of distributive allegories, right? You have union, intersection, and those kind of things.
Yes.
Is there also a way to incorporate the residuals into those diagrams?
I'm not sure. What do you mean exactly by this? This is very interesting for me.
If you go the next step for adding more operations to distributive allegories would be the left and right adjoint for composition. Yeah, these are the residuals. Yeah, and if you use the calculus, those things play an important role if you want to model programs and stuff like that. Is there a way of incorporating them? Freud calls them, I think, division allegories, if I remember correctly.
So what? Maybe I'm not sure, but what make your question thinks about? In the closest things are what what are sometimes called projections, maybe in some other terms. So this means these are kind of similar to what I showed you. I showed you here. So I guess I'm not sure, but this is basically. I mean. Let's say maybe it's simpler to make the example like in REL. Like if you would like to model like an imperative programming language and you want to have guards, then how do you do guards? Let's say you have that some G, so you know that this G is a guards in the sense that is included into the identity.
Okay.
And then you know that if you do G union not G, this is equal to
The identity.
the identity, and then if you do G compose with not G, this is 0.
Yep.
So basically, you can express this in string diagram like this. In tape diagram like this. You're saying.
Yeah,
this-
but that's not really what I mean. What I'm talking
Okay.
about is more about a construction like the weakest precondition.
Oh.
That is
like
normally a
constructing
residual. So
condition. Yes, because you want
dividing from the left or the right in the composition. Well, with respect to the composition.
that's very interesting, because I mean, what I'm thinking about these days is also like some sort of Hor logic.
Yes.
Yes. So it's really something I should look at. Thanks a lot.
Mm-hmm.
Okay. I don't have a good question, a good answer now.
So I think it's time to thank Filippo again for his talk, for his presentation. And we have 5 minutes. In the meantime, Ingo can correct and check if the battery is still